My name is Ilia, and I'm going to talk about detecting multi-step IAM attacks in AWS environments via model checking. So this basically keeps the same topic from previous talk. This work was conducted in Citi Tel Aviv Cybersecurity Innovation Center together with Oded Margalit from Ben-Gurion University. So let's begin with some background. Cloud adoption is on the rise. The share of data stored in the cloud is steadily growing. And naturally, there is a growing concern about the security of cloud applications. AWS, one of the biggest cloud providers, introduced the shared responsibility model, where AWS is responsible for the security of the cloud, the lower level infrastructure and hardware, and the customer is responsible for the security in the cloud, the higher level application data and identity and access management, or IAM. But IAM is known to be very complex and it is notoriously hard to master. And so more than often, we hear in the press about security breaches due to IAM misconfigs. Yeah, that's the same screenshot from previous talk. So now let's take a look at a small IAM misconfiguration. So consider an AWS account with the following resources. There's a role named Alice, and Alice can do many IAM role actions on other roles, for example, reading or updating, but not on herself to prevent immediate privilege escalation. And there's also a bucket named Bob's bucket, and Bob doesn't want Alice to be able to read from his bucket, so there's an explicit deny in the policy, preventing it. So I want to ask, how can Alice nevertheless be able to exploit this configuration and read from Bob's bucket? So Alice can do as follows. She can create a new role with a different name, for example, Carol. Then she can use put role policy action to make Carol super permissive and in particular be able to read from Bob's bucket. Then Alice switches to the new role by doing assume role. And from the new role, she can read any object from Bob's bucket. And observe that this attack involved only documented AWS API, and it still resulted in a privilege escalation. So the vulnerability here is in the IAM configuration and not in AWS. So some tools are already dealing with this problem. Rhino Security Labs company, for example, published an article describing 20+ privilege escalation techniques in AWS IAM. So put role policy action is one of those. And they released Pacu, an open source tool that syntactically scans IAM policies and detects instances of those actions in the policies. And also, AWS themselves developed Zelkova that uses semantic-based automated reasoning. They build a mathematical model of IAM policies, and they attempt to answer if a bucket is exposed to the public. But they check only current configuration, and sometimes an attack can involve several steps. And also, sometimes an attacker can use only a specific subset of permissions, so syntactically scanning policies may also not be enough. So we want to consider another approach, model checking, which is a known technique to check whether a model of a system satisfies certain properties. So we need to formally model a system. In our case, the system is AWS Identity and Access Management from the point of view of an attacker. We also need to define a property to check. In our case, this is the attack target, the ultimate goal for the attacker. For example, reading a bucket, getting administrator privileges, and so on. Then we run model checking, and we can get traces leading to a violation or a satisfaction of a property. And our traces are the multi-step attack vectors. In fact, this approach was already suggested in the context of network vulnerabilities by Ricci and Eman back in 2000. And in fact, in networking, formal methods are often used for attack graph generation. So let's see how we can use it for identity and access management. So our identity and access management model can be roughly divided into 4 parts. First, we have the attacker, which is the encoding of the request, the action performed on some resource by some principal. And the attacker chooses what to perform next, so naturally we must define the action semantics, or the encoding of the transitions from the current state of the organization to the next state based on what action was chosen. So the actions affect AWS organization. So next we must encode all the resources in the organization, all the roles, policies, buckets, information such as what roles are attached to what policies and so on. And the state of the organization affects the outcome of the policy evaluation logic, which is the encoding of all the very complex evaluation rules from AWS documentation. And this ultimately impacts what actions the attacker can perform next. So I like to think of this framework as a puzzle like Sokoban that we may all remember from childhood. So you can think of the attacker as the warehouse guy, the organization as the walls and the boxes. The final storage location of the boxes is the attack target, and the solution to the puzzle is the attack vector that we get. Regarding the action semantics, we do not model all AWS actions, as there are hundreds of services and actions in AWS. So we want to focus only on the means actions, those that either affect IAM directly or indirectly, perhaps because there is some discovered IAM vulnerability, like AWS Lambda. So in total, we modeled around 60 actions, the full list in the paper, all the Rhino Security Labs article actions, and some complementary actions. So, for example, the modeling process was like this for put role policy. First, we read security articles, we recognize that it's a privilege escalation prone action. Then we read, carefully read and understand AWS documentation in order to encode correctly the transition of the organization, what happens after the attacker performs put role policy in the next state. Okay, to encode the policy evaluation logic, first we take all the policy documents, we encode them into formulas similarly to the way it was done in Zelkova. Then we take all the policies of all the resources across our organization, and we bring them together into one big policy evaluation logic formula that is based on the evaluation flowchart from AWS. So we take all the allow and deny statements and combine them together in order to evaluate correctly if a attacker request is allowed or denied. So a few words about our implementation and evaluation. So we implemented this model checking process with Java and the open source Z3 SAT Solver API. We implemented a custom bounded model checking algorithm and also an exhaustive version that keeps logically negating traces until we exhaust all attack vectors for a given configuration. And for our evaluation, we used a large pre-production AWS organization with around 100 accounts, on average 200 different IAM resources in each account. And we ask how does the model checking process detect existing misconfigurations in real-world AWS environments. So to this end, we provided the security engineers in the company with an interface to this model checker. We instructed them how to write properties to check, how to use it. And we gathered 141 requests. And the security engineers mainly wanted to see who can get access to data resources in the accounts, such as buckets or queues. And some interesting observations from the results. here's the breakdown of the attack vectors by length. So indeed, more short attacks than long attacks, and many attacks are even one step, so those are immediate misconfigurations. Maybe some of those attacks are even expected given the configuration, but nevertheless, there are many two-step vectors and above, and those are real IAM privilege escalations. And also here is the breakdown of all the actions performed across all the attack vectors. So we can see that some actions are remarkably common, and there are remarkably common patterns. For example, update assume role policy, where the attacker can change who can assume some maybe very privileged role, and then immediately afterwards assume it themselves. So update assume role policy is a heavyweight permission. Use it carefully in your IAM policies. And yeah, okay, bottom line, security engineers were greatly satisfied with the results. They were able to discover a lot of sneaky misconfigurations, fix a lot of sneaky over-permissive policies. And in addition, we also performed a performance evaluation, and we show that our approach detects attacks of up to 5 steps in large accounts in under a minute. So this model checking process is also scalable enough for real usage. And with this, I conclude my talk. Thank you very much. Happy to take questions.